Hey guys, we're on Unit 4, Day 3. We're going to talk about line reflection strictly today. All right, so we're going to reflect over some lines that look normal, like the x-axis and the y-axis. However, we're also going to reflect over different horizontal and vertical lines, and also a diagonal line called y equals x. So our warm-up is to graph the line y equals x and the accompanying grid. Cool thing is that we have a graphing calculator. And if you go ahead and hit your y equals button, okay, type in x, and then hit graph, you're going to realize y equals x is not a scary line at all. It's actually a very, very simple line. Okay? It goes from the upper right-hand corner of your graph to the lower left-hand corner. All right? It has a slope of 1. Right? And it has a y-intercept of 0. So if we were to go ahead and plot some points, okay, your y-intercept was b0, okay, and then it's up 1 over 1, which gives us this set of points. And when we connect those set of points in both directions, we end up with our line, okay, and it looks just like this. And we're going to reflect over that line today. All right, so going on what a line reflection is. Okay, we've talked about it a little bit. But we're going to talk about it more in depth today. All right, so a line reflection is a transformation in which a figure is flipped over a given line as if in a mirror. Each point of the reflected image is the same distance from the line of reflection as the corresponding point in the original figure. So what that means, if this is my line of reflection and this is my original triangle, okay, the distance from one of my points to the line, let's say that that's 10 units, is going to be the same distance over my line to my new point. That has to be the same distance, okay? And that has to work for all the points, okay? So for instance, if B is closer to my line of reflection, let's say it's, 7 units, then it's going to have to be 7 units on the other side where you can get to your B prime. All right, same thing for C. Okay, going back to our bullets, any point in the pre-image that lies on the line of reflection will remain on the line of reflection. Because if you're already on it, you're not, your distance away from it is 0, so you don't move. These points that remain fixed or do not move are called invariant. Invariant points, okay? All right, so then the next part says that the line of reflection is a perpendicular bisector of each line segment joining a point to its image. So if we go back up to look here, remember how we had this line of reflection here? And remember that this line segment connected A to A prime. Notice how that 10 is equal to that 10. So there's the bisector part. And the line of reflection is going to be perpendicular to that line segment. Okay. And so that's why they call it a perpendicular bisector. Okay. All right. One more thing to talk about in this picture here. Notice that part of your original triangle is already over the line of reflection. So what's going to happen is that this part that's already over still flips over to the other side, and this part that's on this side will flip over to this side. Okay, and so it makes your picture a little bit crazy because the two triangles or the two figures will overlap when that happens. Okay. All right, number 1. It says, in the accompanied diagram, a transformation maps triangle HIJ onto triangle H prime I prime J prime. Identify the transformation. Okay, so if this is your original triangle, and this is your image. Okay, I think that you guys can tell. In fact, I think we've already looked at the same exact picture, but you are taking that blue triangle and you're flipping it over the x-axis, and it's becoming the red triangle. And so when we talk about transformations on a graph, just stating that that's a reflection is not good enough. So we're going to say a reflection over, and we always have to tell what line we reflected over. So over the x-axis. Okay, the notation used for that is a lowercase r and then x-axis. But if you don't abbreviate it, you don't have to use a lowercase r, like for instance, I didn't right here. Okay, but if you notate it, it has to be a lowercase r for reflection. All right. It says, when identifying a transformation as a line reflection, be precise and state that it's a line reflection and state the line that the figure is being reflected over. And we did both those things, so we should have got full credit for that. All right, number 2 talks about graphing BAT, okay? And BAT has vertices at -5, 1, 2, 3, 4, 5, +1. Put a dot, call it B. A is at -1, +1. Put a dot, call it A. Okay? And then T is at -1, +7. 1, 2, 3, 4, 5, 6, 7. Okay? We'll try to use our straight edge if I can find it. I found it the other day. Just not quite sure where I found it. Nope, that's going to draw me a rectangle. I'm going to just try my best at my freehand. All right. If you have a straight edge, I highly recommend using one. Okay. So part A says, on the same set of axes, graph and state the coordinates of triangle B prime, A prime, T prime, the image of triangle BAT reflected over the y-axis. Okay. I also highly recommend using a highlighter and highlighting the line you're reflecting over. I find that helps a lot. Okay. Because they said y-axis, I'm going to go ahead and highlight my y-axis. And I'm going to go ahead and take that triangle and flip it over. So notice we'll start with B since it's the first letter, and B is 1, 2, 3, 4, 5 units to my line of reflection. And so when it goes over, it's going to have to go 5 units over my line of reflection. So 1, 2, 3, 4, 5. This is going to be B prime. A is only 1 unit to my line of reflection, so it only has to go 1 unit over. And when it does, call it A prime. T is also 1 unit to my line of reflection, so 1 unit over would be T prime. And then I'm going to graph it. And there's my new triangle. Okay? And they want to know the coordinates of it. So we can go and say, all right, B prime's coordinates would be, I'll go all the way back to the origin, okay, and count from the origin. And so we'd have 1, 2, 3, 4, 5, 1. And what a lot of people do is they're going to look up and say, all right, I think I know the rule. All I have to do is if I reflect in the y, I change the x. Okay? And so they can get their other coordinates by doing that, or they can continue to count, but A would be at +1, +1. Okay? And T prime will be at +1, +7. Okay? So now part B says write a mapping rule for a reflection in the y-axis. When you reflect in the y, you change the x. Okay, when you reflect in the y, you change the x. All right, so for instance, if I have coordinates of x comma y, and I'm doing a reflection in the y, all I have to do is change the x by putting a negative, leave the y alone. Okay. Part C says connect each pre-image point with the corresponding image point. What do you notice about the line of reflection and the segments you drew? So they really want me to connect T and T prime, which I kind of already have, but I'll make it a yellow line. Connect B to B prime and connect A to A prime, which is already kind of under there. All right. So they want to know, what do you notice about those yellow line segments and your yellow line of reflection? Well, we talked about it up there, but the line of reflection is the perpendicular bisector to those segments. Okay. Part D asks if there's any invariant points, and if so, which ones? Did any point not move? All points move, right? B, A, and T all moved to a different location. Nobody's coordinates stayed the same. So are there any invariant points? And the answer is no. All points moved to a new location. Okay. Part E says, what do you think of the mapping rule for reflection in the x-axis would be? Well, if you reflect in the x-axis, you change y. So your coordinates of x comma y would be mapped onto still x, but change the y. Okay, and there would be your mapping rule. All right, I will see you guys on the back side of notes to finish this off.